Thank you for the introduction and thank you for having me here. I'm really happy to be back to present the work with Daniel and Ethan. So the main focus of my second talk is to construct RAM FHE and supply the remaining part of the algorithm. So I'm just quickly recapping the motivating example of private search. We want to perform encrypted search. We don't want to use circuit FHE. That's too slow because circuit size depends on input data size. And Google's input is like the whole internet too slow. Okay, so our solution is to provide FHE in the RAM model. And Ethan has explained that without preprocessing, that's a lower bound. So the Google in our solution preprocess the data structure, all the data on the internet into a data structure. It's one time upfront for all users. And then whenever the user Alice here comes in, she can encrypt her own query using her secret key. I mean, this secret key doesn't need to be tied to Alice. She can always sample a new fresh secret key for every query. And then Google can carry out this encrypted query by looking at a few locations in this preprocessed data structure. And Google has to put the internet into some data structure anyway to facilitate the search. So toward the construction, the RAM FHE to achieve efficient private search, I need two building blocks. They are presented in Ethan's talk, but I'm just quickly recapping them. It's just two slides. The first building block is doubly efficient PIR. Ethan showed the construction at a high level. So here is the really high level abstraction. We have a database like the movies on Netflix. We have the user Alice wants to watch a movie, and to facilitate private movie watching, Netflix preprocess the database into data structure, and then this solution, our solution of PIR, can allow Alice to encrypt her movie index I, and then just use a few locations in the preprocessed data structure, and Netflix can respond with the movie Alice wants to watch. So Ethan also explained this is a weaker abstraction than RAM FHE in the sense the functionality is more restricted. It's just index and retrieve the desired index. There's no computation, and in RAM FHE we have the computation in previous slide. Okay, that's the first building block. We achieved the nice space and the time trade-off, although we have already discussed the practicability. I'm going theoretically, so we are good for now. My second building block needed is also shown in the previous talk. That's algebraic homomorphic encryption. It is a homomorphic encryption in the sense that we want to perform homomorphic multiplication and addition. But we want our new nice property so that the ciphertext space is a polynomial ring. And in polynomial ring, we have ring operations, multiplication and addition. They are polynomial multiplication and addition. We want our homomorphic operations exactly the ring operation to use the data structure of polynomial evaluation. And these are the two building blocks I will need later in my construction of RAM FHE. And in particular, this algebraic operation cannot use public key like bootstrapping techniques exists in FHE constructions. So this scheme is like necessarily, or we don't know how to do it. It's bounded degree in multiplication. Okay, and now this is a RAM FHE with notations. So in RAM FHE, we want to compute a program P in random access machine model. This P takes two inputs. One of the input is the public database of Google. And in RAM FHE, we preprocess, and then after this one-time preprocess, user comes in with private input, and what we want to do is encrypt this input and do homomorphic evaluation on this program P. By homomorphic evaluation, what we want is to compute this RAM program, like the computation of this RAM program P on input X and Y. But Google is given with the program P and only this preprocess of Y and the ciphertext. So we need some algorithm that I will show later to carry out the homomorphic evaluation. And our goal is to be efficient. We don't want to pay the circuit size of the standard circuit FHE. So the running time of this homomorphic evaluation should be close to the insecure running time of the RAM program P. Okay, that's our model and our efficiency goal. And let me first expand a little bit. What do I mean by a RAM program P? This program P has two input, X and Y. The input is read-only, but this program P, without any encryption, need to use some internal memory to, like a scratch tape, to read and write the intermediate computation. And by random access machine model, I mean, this program P has random access to not only Y, P also have random access to the input X and the internal memory. Particularly, the internal memory has to be read and writable, and compared to the input is only read-only. So the most challenging part is to make this homomorphic, and by homomorphic evaluation, we are encrypting this secret input X. And that means the memory is necessarily encrypted. Otherwise, the intermediate computation can reveal some secret about my input X. And to make it efficient in the evaluation, it's quite challenging because things are encrypted, and then we want efficient access. And we also want to write. That's too much in construction. So in this talk, I will mostly focus on the simpler case. We assume this program P only has random access to the public input Y. And this is already non-trivial and sufficient for our motivating example, like a private Google search, because in Google search, the X is user's query. It's just a short string. We don't really need the efficient random access. And in search, the memory is so small, we don't need the random access. And that makes the construction simpler and easier to understand.
In the paper, you would...
in the paper, we construct all of them. Like in Ethan stated the theorem statement, but I mean the statement itself is already dependent on like 3 or 4 parameters, and it's not very easy to touch. So yeah, so that's our
Why the memory is small?
Oh, so I don't really understand Google search, but I suppose Google search is something similar to binary search, right? And in binary search, the memory during my computation is really just my looking at one location and remember my location to go to the next.
It's bounded by the runtime, right?
Yes. So
Yeah.
yes. So the running time of P can be much smaller than X and Y, and the memory can be much smaller. Yeah, good question. So that's our model. I'm going to expand this simpler situation in the slightly more formally using step computations. That's typically how we formalize a computation in the RAM model. So we have input X, it's a small input, so we just send it directly to a, say, constant size CPU step circuit. You can think it's a universal circuit that takes in the description of program P, or you hardwire the description of P into the circuit. I mean, the program P is short also, so it doesn't matter. And all this is plain text computation. The CPU step just want to read some location I from the large long input of Y. And that's the only random access we allowed in this simpler case. That's the random access to Y. And then the cost of this running time of program P is just proportional to the number of CPU steps we are using. And that's the computation without any encryption, without any security of program P. And Ayush asked a good question about the running time of P, and I'm just supposing it's like a worst case time here. And yeah. No, okay. So let me try to continue with making it a homomorphic evaluation. So in a homomorphic evaluation, first the input X is secret, so we want to encrypt it. And looking at this CPU step circuit, we know it's some circuit, and we have good FHE for circuits developed in the last decade. So our first attempt is just to apply standard circuit FHE on this CPU step circuit and obtain encryption of the location. So that's the standard circuit FHE, right? You take input encrypted, you output whatever output encrypted. And to continue with my next CPU step, we really want to get the data entry encrypted as FHE ciphertext indexed by the location. But here, this is the main challenge of RAM FHE, because naively, I could get this ciphertext by instantiate a large circuit and read all the input Y and use FHE to get this, but that's too slow. So to overcome this challenge, there is only one previous result to that. The result is using a nice observation that is the similarity between this and the PIR building block we just showed, right? Like in PIR, we want to get the data and hiding the location of this data. And here we want to get this data and we don't want the server learn the data. But there is a mismatch, and that's a big mismatch. In PIR, the location is held by the user Alice, and we assume Alice can sample some secret key, secret randomness to make a PIR query and send it to the server. But here, everything here on this slide is homomorphically evaluated by the server. And how do we make a query using this guy? It's even encrypted and still make sure the server doesn't learn anything. So the previous result is kind of using this approach and push it through in the following way. So suppose we have a doubly efficient PIR, and we did indeed have in our first talk, we constructed and the doubly efficient PIR says you can preprocess Y upfront, and then somehow you can access it efficiently later. So we preprocess it, and we do FHE evaluation for one CPU step. Then the previous approach do the following. They say, okay, it's encrypted in FHE, so we decrypt it using FHE secret key. But that's horrible because this is on the server. We cannot give the secret key to the server. So their approach is Okay, let's instantiate a big black box. Obfuscation, which presumably can hide this secret key in the view of the server. And then within this black box, we can suppose this black box can hide everything. Then the idea is, okay, we get a location, then we can use another secret key of whatever PIR needed, and do the PIR query, get the query out of the black box, and resolve this query using PIR again, get back its a response of correct PIR, and then we encrypt this guy using FHE again to get FHE ciphertext. But this solution is really unsatisfactory for 3 reasons. First, obfuscation is heavy anyway. We don't know efficient construction of obfuscation. Second, we are hiding a lot of secret key, secret randomness in the black box. So that makes construction and the security proof quite complicated. And third, the obfuscation is actually in previous proof, it was heuristic. So it's not even IO, it's something, it's not even virtual black box. So
Ideal obfuscation, right?
yeah, it's ideal obfuscation. So that's something, unfortunately, we don't have any candidate construction. So it is a extremely strong assumption. I mean, we don't have any construction for ideal obfuscation for even this specific task. So yeah, that's an extremely strong assumption. And in this work, we killed this assumption and replace it with standard assumption ring LWE. And we make this quite simple, this construction quite simple with our doubly efficient PIR. And our main contribution is the following. In the previous picture, in the previous slide, there are 2 homomorphic encryption schemes. The first is FHE. We use FHE to evaluate the CPU circuits. And the second is the ASHE, algebraic homomorphic evaluation, that is used to perform doubly efficient PIR queries. In particular, the queries are indeed the ASHE ciphertexts of in the construction of PIR. So our main observation is they are, I mean, they have totally different ways to perform the homomorphic evaluation, and they have different constraints. But their ciphertexts, the format of their ciphertexts are almost the same, and we can switch the ciphertext back and forth between the 2 words. And we can do this using ring LWE, like the same assumption we used for ASHE, or the same assumption ensure approximate GCD. Plus circular security because technical details, and also because we need that for FHE anyway. Okay, so with this hybrid scheme, going back to the picture, things are simplified a lot actually. So the server preprocess, that's the same, and then client encrypts the private input, that's the same. And everything happening evaluated on the server. Server use FHE evaluation. Then when the encryption of locations comes out from the step, the server switch this ciphertext into a PIR query for the location. And then the server can at the same time resolve this query itself on the server and get back to a encryption of the desired data entry to continue with the next CPU step computation. So here we need to switch back to FHE ciphertext again. So putting it into a big picture, that's the construction of our scheme. So it's really simple. Whenever I want to evaluate a CPU step circuit, I use FHE evaluation. And when this CPU wants to access some data entry through random access, we just switch the ciphertext and use the algebraic evaluation. And this is really the construction of our RAM FHE in the simpler scenario, where we just need random access to the public input Y. And this is a good pointer to escape any question.
I still don't understand how they can like switch back and forth.
So, I mean, thinking about approximate GCD, like described in Ethan's talk, the approximate GCD ciphertext in ASHE is like an integer, right?
Yeah.
It's an integer that is encrypted from A times S plus some error plus message. It's an integer. And we achieve ASHE by algebraic multiplication on this integer, integer multiplication. That's what I do for ASHE. When I go back to FHE, I will need to use bootstrapping in FHE. That means in the FHE construction of approximate GCD, from approximate GCD, the ciphertext is still the same format, A times S plus error plus some message. And the only difference is in the world of FHE evaluation, we are using bootstrapping to reduce the error and slash down the degree or something. I mean, reduce the error generated during whatever multiplication during the process. And then the ciphertext is the same format, it includes the same plain text.
Okay.
Yeah.
And then essentially, we need to set the parameters that we can perform exactly the polynomial that we want on the PIR side, plus one extra
Bootstrapping.
bootstrapping.
Yes.
Get back to like a fresh thing.
To get back to small error. And I mean, this bootstrapping to get back to small error is needed by FHE anyways, so we are good with that. Okay, so I continue on a super high level construction of our full FHE with random access to encrypted input X. That's a large private input encrypted by the user. And the construction is extremely similar to Y, except that the user encrypt X upfront using a pseudo-random function, like a one-time paired X with some pseudo-random string generated from pseudo-random function. Send this one-time paired message to server, and the server can use FHE to do whatever we do on Y, like decrypt the ciphertext of the X inside FHE to get whatever we want. Providing random access to read-write memory is more challenging because now we are not only encrypting the memory, we also want to update the efficiently write to the memory.
It's a small size memory, right?
No. This is the full construction. So the program can use large memory, and we still want the homomorphic evaluation time to be proportional to the program running time in RAM model. And if we convert the program to circuit model, the circuit will take at least a quadratic in size compared to the RAM running time in RAM model. So this quadratic saving is one of the purposes we want to save here.
Or I guess maybe like an additional reason why you might want random access to the memory is like maybe you want to have many hops and computations, and maybe there's a similar output.
Yeah.
Like this memory can be from computed, and then next homomorphic evaluation can reuse the result. Yep. So that's a very good question. But for the constraint of time, I'm not really going into details of this rewrite memory.
Roughly speaking, do you have to modify the data?
Yes, we do. I will show you at a very high level. So the question is that even the memory is not encrypted, we already need a new data structure to support the writes. And that unencrypted memory is actually similar to PIR. We call it updatable PIR. And I'm going to show you the simpler unencrypted variant of updatable PIR instead of the whole memory encrypted and there's too many layers. So, I mean, updatable PIR itself is already a standalone and useful abstraction, just like the PIR. Say, let's take the example of Netflix. The Netflix may have already processed all the movies into a data structure, but later the Netflix wants to update some movie I to the newest version, right? And the query depends on the data structure, and we want to make updates on the data structure, also reflecting the updated movie. And we want to do this update fast by locally modifying a few locations in the computed data structure. That's the notion of updatable. And as is mentioned, this update is public, like publicly the movie is updated. We are not hiding it, and it is known to the server anyway. The point is we still want to support efficient queries, efficient movie watching from Alice. Like Alice wants to watch the updated movie I later after the update. Alice should be able to look at a few locations in the updated data structure and get to watch the movie. There is a slightly paradoxical thing in the first slide here, because if my reader locations are only a small set and my update location to the same movie is a small set, the two sets must overlap, otherwise the Alice cannot get the newest version of movie I. But if they overlap, that might leak information about I to the server, because the server sees the overlap. And our construction shows no, it's possible. And the reason it's possible is because first, we have construction, we prove it is secure. Second, the overlap is very small. That's not even enough information for the server to derive that Alice is watching I. Okay, so the construction is very similar to the hierarchical ORM construction of Doubly and Ostrowski. So the intuition is whenever I want to update, I mean, first we have log-n levels of data structure. Each data structure, I mean, database is preprocessed correspondingly. And whenever I want to update, I only update to the smallest level. These levels are growing geometrically, so I can, when the smaller level fills up, I can merge it down, and that will save me time in the amortized sense. So I'm not going into details. You can probably understand it when I flash the slide through. Question?
So the worst case doesn't change, right?
Yeah, so there are writing time or update time and the read time. For worst case, I guess you are saying in the worst case, after I update n times, I will need to preprocess the database of size n. Yes. Okay. And let me flash my slides and animations through and go to your question. So this is what I'm saying when the updates comes in, and keep doing the merging this new updates down the levels, and it's growing geometrically, so there are enough space to amortize it. And after to the I writes, I only need to reprocess a level at of capacity to the I. So the amortizer cost per update is like n to the epsilon, because for each preprocess I spend 1 plus epsilon on the exponent. Yeah, but talking about worst case time, this worst case time can be de-amortized. So really the worst case time can be bring down to this n to the epsilon. And the read time is roughly the same as performing standard DE query. We are just searching the index, the desired index I through all these log n levels, which pays a polylog n, roughly polylog n extra vector on the query time. Yeah, so this is the construction for RAM FHE and the slightly weaker variant, updatable PIR. I am going to conclude. So far, Ethan's talk and my talk covers all the new ideas and the main contributions of our work. We constructed the PIR and the RAM FHE from standard assumption and the preprocessing. Like Ethan told us in previous talk, the preprocessing is necessary to work around the lower bound. And our preprocessing is the best we can hope for. That's until the preprocessing can be performed by a potentially malicious server. There are open questions like we have discussed the practical efficiency and can we bring other assumptions? Maybe let me first take questions here for our techniques, and I will then show you on board the beautiful construction of Katalaya and Lumens. So questions first.
Can you use it to like do other things like technical RAM? Can you use our FHE somehow to bootstrap to build technical RAM starting from technical circuits?
What circuit?
So let's say you have functional encryption for circuits,
Mm-hmm.
and then you have this new FHE construction.
Yes.
Can you use it to do functional encryption for
The
RAM
program.
program?
Yes. I mean, like there are a couple of papers we saw in the last year that really constructed the functional encryption for RAM
But
code.
they're very inefficient, so they're not very like direct or.
No,
they use
yeah,
like-
good question, good question. So
I
they-
got a co-author on one of them actually.
Oh. I don't have a good answer, so first you can plug in our better doubly efficient here.
Yeah.
But I don't know much beyond that because functional encryption kind of in the circuit model kind of need
I was just wondering if there are direct applications that you thought of. Direct, like just directly find.
So one direct application that we thought about, and we kind of put a section in our paper is that we can do multi-hub RAM FHE, like every party just preprocess his own or her own data, and then this never mind. So this encrypted memory with the capacity of random access that I didn't show you can be passed around or reused in many hubs, right? Like say each of us has a big data, and we just want to compute very fast some short logarithmic computation. Then we just each pay 100% on our data, then we are good to perform any computation.
I guess the nice thing about this is like almost FHE, so
Yes.
perhaps you could also do like multi-key version, multi-key FHE for RAM and things like this, correctly.
So first, yes, as long as my
Like you can have key switching.
yes,
going
yes,
on.
yes, yes. I mean, even without the key switching, we already can participate with like Google is preprocessing once and participating in many homomorphic evaluation with different keys, right? So this preprocessing really works with many different keys. They don't need, each instance has to agree on the key, but the different instance can reuse the same preprocessing particular key. Yeah, I mean, there are like some applications we come up with, but I mean, this result is just exciting enough.
Yeah.